Are you ready? Are you excited? Okay, so in this episode, I will be going far beyond the bedrock of the soil horizon, examining the geologic structure and composition of the Earth's interior, down to the core of our planet. But first, let us define what bedrock is. Bedrock is the solid, continuous layer of rock that forms the Earth's crust underlying looser surface materials like soil, sand, and vegetation. Bedrock can be exposed to the surface by soil erosion, weathering, and tectonic uplifts. So we can safely say that the bedrock is the foundation of Earth's crust. Let's now delve into the structure of Earth's interior, which has different distinct layers, starting with the lithosphere, which is the rigid outermost part of the Earth that includes both the crust and the uppermost part of the mantle, which is termed the lithospheric mantle, and it is rigid. The mantle is about 2,900 kilometers thick, which is 1,800 miles thick, and is composed of mafic minerals, similar to olivine, which is a silicate of magnesium and iron, and may resemble ultramafic rocks, like peridotite. Between the crust and the uppermost part of the mantle, there is a region or boundary called the Mohorovičić discontinuity. It represents a fundamental division within the lithosphere, separating the relatively lighter crust from the denser uppermost part of the mantle. The crust is defined as the outermost solid layer of Earth, varying in thickness. It is generally about 8 to 40 kilometers thick, but that is a partially correct measurement because its composition consists of the continental crust, which is about 25 to 70 kilometers thick, and has both felsic and mafic rock zones, which is thicker, less dense, and is rich in silica, and is composed of granite, while the oceanic crust is thinner, about 5 to 10 kilometers thick, and is less dense, and it is composed of mafic rocks, such as basalt. Then there is the asthenosphere. The word asthenosphere is derived from the Greek root word asthenos, meaning weak. The asthenosphere is not liquid, but its temperature is about 1,400 degrees Celsius. This is the layer of the upper mantle, specifically the lower, weaker and more ductile section, which is soft and behaves like a plastic, that is located just beneath the lithosphere or beneath the lithospheric mantle. It consists of hot, dense rock rich in magnesium and iron, such as peridotite, that contains minerals like olivine and pyroxene. The high temperature in the asthenosphere caused the rock to be semi-molten or partially molten and is capable of slow flow, allowing the tectonic plates that makes up the rigid lithosphere to move over it. Or another explanation is that because it is ductile and behaves like a viscous, slow-moving fluid, it is able to deform under high pressure and enables the movement of tectonic plates. However, the real driving force of tectonic plates are convection currents in the asthenosphere. Then there is the mantle transition zone, or MTZ, which is a layer in the Earth's mantle, in particular between the upper and lower mantle, approximately between 410 and 660 kilometers in depth. The transition zone contains the mineral ringwoodite, which is a form of high-pressure olivine that can store considerable amounts of water within its crystal structure. This deep water in ringwoodite is crucial for understanding Earth's water cycle and influences the hydrology and dynamics of the mantle transition zone. The existence of water in ringwoodite was confirmed by a natural inclusion found in a Brazilian diamond. The mantle transition zone plays a crucial role in the Earth's internal structure, moderating heat flow and material circulation, and is a significant repository for water. Then there is the lower mantle, which is primarily composed of magnesium and iron-bearing silicate minerals, predominantly the high-pressure forms of olivine and pyroxene, such as bridgmanite, ferropericlase, and calcium silicate perovskite. Despite of the lower mantle being extremely hot, it is solid due to the immense pressure from the layers above. The high temperatures make the silicate materials ductile, allowing for the slow creeping motion or convection currents in the lower mantle that occurs when heat from the core causes the mantle material to become less dense and rise, spread, cool, and then sinks back down in a continuous cycle over geologic timescales. And this is the driving force behind plate tectonic movements, as mentioned earlier in the video. Now let's briefly talk about plate margins. Firstly, there is converging plates. Now at a converging plate boundary, an oceanic plate subducts, and water is squeezed from the subducting sediments and minerals. The water then migrates into the overlying mantle wedge, which lowers the melting point of the mantle wedge, or mantle rock, causing it to melt and form molten rock or magma, which form into pockets or chambers in the crust. or we could say the molten rock, collects into these underground reservoirs before rising to feed volcanoes on the surface, because the magma is less dense than the surrounding rocks. So it rises upwards through cracks and weak points in the crust, leading to volcanic activity and forming volcanoes on the surface. It is also important to note that at converging plate margins, when continental plates collide, they crumple upwards to form massive mountain ranges. Or when continental plate collision occurs, the crumpling, folding and uplifting of the crust takes place to form mountain ranges. Or in other words, when continental collision occurs, rock layers making up the crust become deformed and compressed into folds to form mountains through the mountain building process called orogeny, such as the Himalayan mountain range. At another plate boundary called diverging plate margin, two tectonic plates move or split apart from each other, causing magma to rise from Earth's mantle and solidify, creating new crust and lithosphere. An example of this is mid-ocean ridges, or the Mid-Atlantic Ridge, where the oceanic plate splits or pulls apart in a process called seafloor spreading, forming a chain of underwater volcanoes, and also in continental rift zones like the East Africa Rift, where the continental crust is being pulled apart. At diverging plate margins, earthquakes and shield volcanoes are common. Hydrothermal vents, often called black smokers, occurs at mid-ocean ridges, spewing out metal sulfide. At transformed plate boundaries, however, tectonic plates slide horizontally past each other, causing earthquakes. This type of boundary is also called strike-slip fault, like the San Andreas Fault in California. Okay, so now we are venturing into a zone of Earth's interior called the Weyert-Gutenberg discontinuity, or the core mantle boundary, CMB. It is a significant boundary deep within the Earth's interior at a depth of approximately 2,900 km, which marks the transition from the solid lower mantle to the liquid outer core, or simply put, it is a boundary between the lower mantle and the outer core. Both the inner and outer core are termed the centrosphere. The outer core churns, rotates or spins and is composed of liquid iron and nickel. Now the flow or movement of the liquid iron produces electrical currents that generates the Earth's electromagnetic field, which shields our planet from harmful solar radiation. Now the inner core is composed of solid iron and nickel. This long-held understanding that the inner core was a simple, rigid solid sphere has been adjusted or refined, because recent seismological data has suggested that its near surface is far more dynamic and malleable than previously thought, even changing its shape and potentially influencing Earth's rotation and electromagnetic field, and is susceptible to change and viscous deformation, changing its shape. And so even within the inner core, there are signs that even more complex structures of its internal composition is still developing. Now, the Earth's outer core has been estimated to range in temperatures about 4,000 to 5,000 degrees Celsius and extends from the core mantle boundary about 2,189 km, which is about 1,195 miles deep, to 5,150 or 3,200 miles deep, while the inner core begins at the inner core boundary approximately 5,150 km deep, extends to Earth's center at around 6,371 km or 3,959 miles deep, and the inner core's temperature is about 6,000 degrees Celsius. Okay, so I know you have a question. How do we know that the Earth's interior is made of distinct layers? The answer is seismic tomography. This scientific technique uses seismic waves or earthquake waves from earthquakes to image the Earth's interior, similar to a medical CT scan. By measuring how wave speeds change as they travel through different materials, slower in hotter or less dense rocks, faster in cooler, denser ones, geophysicists and seismologists can create 3D models of Earth's structure. Or in other words, seismic tomography produces 2D and 3D images of Earth's interior by using seismic waves to map subsurface structures or layers. By analyzing seismic waves from earthquakes or explosions, geoscientists can create models that reveal variations in temperature, density, and rock composition, providing insights into processes like plate tectonic movements and mantle dynamics. So to better understand, think of the P and S seismic waves. The P waves are primary waves that pass through the mantle and core, while the S waves, which are secondary waves, only passes through the mantle because they cannot travel through liquids. The fact that the S waves are blocked by the outer core, combined with the altered paths of the P waves, provides crucial scientific evidence for the liquid nature of the Earth's outer core. But it goes even further, because volcanologists and geochemists studying volcanic activity on the surface examine the geochemical composition of volcanic magma and lava flows, and study the mineral crystals they produce, such as olivine or peridot, which gives a great insight into Earth's interior, and also mantle plume activity, which is the driving force behind hotspot volcanoes, gives great insight into Earth's interior as well. But that is for a future geoscience episode. This entire episode can be summed up in one word: the geosphere, which encompasses all rocks, minerals and soil, as well as the dynamic processes that shape the Earth's surface, such as plate tectonics, weathering and erosion. Or put simply, the geosphere refers to the solid rocky parts of the Earth, from surface landforms and sediments to its interior layers like the crust, mantle and core. This video is an update to a previous documentary I did called The Process of Orogeny and Plate Tectonics. And so the information presented in this video is based on our current understanding and interpretation of seismological and geophysical data, and our understanding of such data can be refined, adjusted, increased, clarified and/or changed in the future as new scientific techniques are developed and as new data is gathered. Or in other words, while Earth has 4 main layers, the crust, mantle, the outer and inner core, the specific details of these layers, especially the inner core's behavior, are subject to ongoing refinement as geoscientists gather and interpret new data from deep within our planet. So stay tuned in to the Soil Mineralogist channel for more geoscience updates. Okay, so here are some bonus or additional images, diagrams and a review of the Earth's internal structure that is made even simpler, so that everyone watching, especially for the young children and adults viewing this documentary at home, so that we are completely clear. First, there is crust, and it is the outer, most and thinnest shell of the Earth, while the mantle is made of hot, semi-solid rock that flows really slowly, kind of like caramel when you heat it up. This slow movement is what drives those tectonic plates around on the surface. Now, if you could somehow dig even deeper, you'd hit the outer core. This layer is geologically incredible. It's made of liquid iron and nickel, and it's super hot, like 4,000 to 5,000 degrees Celsius, while the inner core's temperature is about 6,000 degrees Celsius, a temperature comparable to the surface of the sun. The movement of this liquid metal creates Earth's magnetic field, which, by the way, protects us from a ton of solar radiation. So thank you, outer core. And then, at the very center, you've got the inner core. This is a solid ball of iron and nickel, about as hot as the surface of the sun. But here, even though it's crazy hot, it stays solid because of the immense pressure from all the layers above it. It's like the ultimate pressure cooker down there. So, to recap, crust on the outside, mantle in the middle, then the liquid outer core, and finally, the solid inner core at the center. Each layer is completely different, but they all work together to make Earth the planet we know and love. And here's a fun fact: we've never actually drilled past the crust. Most of what we know about the internal structure of our planet comes from studying earthquakes, volcanic eruptions, as well as mineral crystals produced from cooling of magma deep within Earth's crust, or from the cooling of lava on the surface, and as well as seismic waves. So, there's still a lot of geological mysteries left to be discovered by geoscientists about our dynamic planet, because we have barely scratched the surface. So stay tuned in for more geoscience episodes like this one, and subscribe to the Soil Mineralogist channel.